Dear learners, in this section, we are going to discuss about subgroup generated by a subset. In previous modules, we have already defined the structure of a subgroup and also learned some properties of subgroups with some examples. So, in this module, we can easily able to understand that how the subgroup is generated by a subset. For your clarification, some important theorems and examples are explained here. Some more interesting facts about the generating sets of different groups are also discussed briefly. Now, let us see the definition first. The definition is, let S be a non-empty subset of a group G. A subgroup of G is said to be generated by S if it satisfies the following two conditions. The conditions are, S is the intersection of all subgroups of G containing S. Next one is, it is a subgroup containing that subset S such that the subset is a generating set for the subgroup. Moreover, the subgroup generated by a subset S is denoted by this symbol. Let us see the next note. A generating set of a group is a subset such that every element of the group can be expressed as the combination of finitely many elements of the subset and their inverse under the group operation. More generally, if S is a subset of a group G, then the subgroup generated by S is the smallest subgroup of G containing every element of S, meaning the intersection over all subgroups containing the elements of S. Since we know that intersection of subgroups is again a subgroup. Equivalently, it is a subgroup of all elements of G that can be expressed as the finite product of element in S and their inverse. Note that, suppose F is the family of all subgroups of G which contains S. Since G contains S, it is the member of this family, so F is not empty. Let H be the intersection of all members of F, then H is a subgroup of G and it contains S because S is contained in every member of the family F. If K is any subgroup of G containing S, then K belongs to F and H is a subgroup of K since H is the intersection of all members of F. Thus, H is the smallest subgroup of G containing S. That is, H is the subgroup of G generated by S. Consequently, the intersection of all subgroups of G which contains S is the subgroup generated by S. Now, given a subset S of a group G, it is possible that G itself a subgroup generated by S. Then, S is called a set of generators of G. For example, if G is a cyclic group generated by A, then S is equal to singleton set A is a set of generators of G. Here, however, S is a singleton. Let's have a small discussion in the group of integers under addition about its generating sets. Do you think does Z plus have two generators but infinitely many generating sets? The answer is yes. We can say the group of integers Z under addition has only two generators, namely 1 and -1. However, Z can also be generated by any set of relatively prime integers. For example, in the group of integers under addition, the two element set 2, 3 is a generating set. To see this, note that every integer can be expressed as a sum of 1s and -1s, and both 1 and minus 1 can be expressed in terms of 2 and 3. That is, in 2 alpha plus 3 beta, we can replace alpha and beta with 1 and minus 1. Vice versa, we get 1 and minus 1 like this. 2 minus 3 is equal to minus 1 and 3 minus 2 is equal to 1. Let us find out the form of the smallest subgroup containing S in the next theorem. The theorem is, if S is any non-empty subset of a group G, the subgroup H of G generated by S, where S is the set of those elements of G which are finite products of integral powers of elements of S. Let us prove this. Let K denotes the set of all finite products of integral powers of elements of S. Then clearly S is the subset of K is the subset of H. If we prove that only K is a subgroup, then we will get K is equal to H, since H is the smallest subgroup containing S. It is obvious that a product of elements in K is again in K. Further, for any x belongs to K, we have x as a product of K I power L is for I is equal to 1, 2, and so on K, and L is equal to 1, 2, and so on K, with AI belongs to S and L1, L2 and so on Lk are some integers, so that x inverse is equal to inverse of product of A I power L is which is also belongs to K. Thus, K is a subgroup as we require. Let us see the remarks. If G is the generator of S, then we say that S generates G, and the elements in S are called generators or group generators. If S is the empty set, then generator is the trivial group identity. Since we consider the empty product to be the identity, let T be the set of all transpositions in the symmetric group Sn. Since every sigma belongs to Sn is a product of transpositions and the members of T. So, we can see that Sn is generated by T. Let's clarify this with an example. Consider S3 is equal to E cycle 1, 2, cycle 1, 3, cycle 2, 3, cycle 1, 2, 3. Let A is equal to cycle 1, 2 and B is equal to cycle 1, 2, 3. Then B square is equal to cycle 1, 2, 3 into cycle 1, 2, 3. Here 1 goes to 2 and 2 goes to 1, implies 1 goes to 3. Next 2 goes to 3 and 3 goes to 1, implies 2 goes to 1. Similarly, 3 goes to 1 and 1 goes to 2, implies 3 goes to 2. So, finally, we get B square is equal to the cycle 1, 3, 2. The similar way we can find B cube, where B cube can be written as B square into B. We have already known that B is equal to cycle 1, 2, 3 and B square is equal to cycle 1, 3, 2. So, B square into B is equal to cycle 1, 3, 2 into cycle 1, 2, 3 is equal to identity. 1 goes to 2 and 2 goes to 1, implies 1 goes to 1. Next, 2 goes to 3 and 3 goes to 2, implies 2 goes to 2. Similarly, 3 goes to 1 and 1 goes to 3, implies 3 goes to 3. So finally we get the identity permutation. Then the product of the permutation A and B is AB is equal to the cycle 1, 2 into the cycle 1, 2, 3 is equal to cycle 1 into cycle 2, 3 is equal to cycle 2, 3. Now we will find BA is equal to cycle 1, 2, 3 into cycle 1, 2 is equal to cycle 1, 3 into cycle 2 is equal to cycle 1, 3. In terms of A and B, therefore, the elements of S3 can be expressed as A, B, B square, B cube, AB and BA. Consequently, the set AB generates S3. Let us see the generating set of some interesting groups as the following results. Result 1. For n is greater than or equal to 2, Sn is generated by its transpositions. The result 2 is for n is greater than or equal to 2, Sn is generated by n minus 1 transpositions, cycle 1, 2, cycle 1, 3 and so on, cycle n minus 1 n. Let us prove it. By result 1, it suffices to show each transpositions. Cycle AB in Sn is a product of transpositions of the form cycle I plus 1 where I is less than n. Since cycle AB is equal to cycle BA, without loss of generality assume A is less than B. We will argue by an induction on B minus A that the cycle AB is a product of transpositions, the cycle I plus 1. This is obviously when B minus A is equal to 1, since the cycle AB is equal to the cycle A plus 1 is one of the transpositions we want in the desired generating set. Now suppose B minus A is equal to K is greater than 1 and the result is settled for all transpositions moving a pair of integers whose difference is less than K. Consider the formula cycle AB is equal to cycle A plus 1 B, cycle A plus 1. The first and third transpositions on the right hand side lies in our desired generating set. The middle transposition permutes a pair of integers with differences B minus A plus 1 is equal to K minus 1 is less than K. By induction, cycle A plus 1 B is a product of transpositions cycle I plus 1. So, cycle AB is as well. The next result is result 3. For n is greater than or equal to 3, each element of An is generated by 3 cycles of the form the cycle 1 I j. Result 4 states that for any n is greater than or equal to 3, each element of An is generated by 3 cycles of the form the cycle 1, 2, I. Let us prove this. For n is equal to 3, the only such 3 cycle is cycle 1, 2, 3 and we know A3 is equal to the set of the cycle 1, cycle 1, 2, 3, cycle 1, 3, 2 is generated by the cycle 1, 2, 3. We now take n is greater than or equal to 4. Since the cycle 1, 2, I the whole power minus 1 is equal to the cycle 1, I, 2. Each 3 cycle in An containing 1 and 2 is generated by the 3 cycles of the form the cycle 1, 2, I. For a 3 cycle containing 1 but not 2, say cycle 1ij, and cycle 1ij is equal to cycle 12j, cycle 12j, cycle 12i, cycle 12j. By using the previous results, we can easily say that each element of an is generated by the 3 cycles of the form the cycle 1ij, and we have done. Let us find out the generating set of GL of n comma r, where r is the real numbers, in the next. The fifth result is the group GL of n comma r is generated by elementary matrices. The proof is fix A belongs to GL of n comma r. It is reduced in a echelon form as nothing but a identity matrix In. The only n by n invertible reduced row echelon matrix. Elementary row operations correspond to left multiplication by an elementary matrix. So, there are elementary matrices E1, E2 and so on Ek such that E1, E2 and so on Ek into A is equal to In. Therefore, A is equal to Ek inverse and so on E2 inverse, E1 inverse. The inverse of an elementary matrix is an elementary matrix. So, A is the product of elementary matrices. The following table summarizes some of the generating sets of the groups Sn, An, Sl of 2, z integers, Gl of n, r real numbers and Sl of n, r real numbers. See this table, it is categorized as group, generating set and size. If the group is Sn, n is greater than or equal to 2 and the generating set is cycle of ij's, then the size is n into n minus 1 by 2. The cycle 1, 2, the cycle 1, 3 and so on the cycle 1n, then the size is n minus 1. If the generating set is the cycle 1, 2, the cycle 2, 3 and so on the cycle n minus 1 n, then the size is n minus 1. We are seeing the group Sn, n is greater than or equal to 2. If the generating set is the cycle 1, 2, the cycle 1, 2 and so on n, if n is greater than or equal to 3, then the size is 2. Next you try to tell the cycle 1, 2, the cycle 2, 3 and so on n, if n is greater than or equal to 3, then the size is, yes, you are right, this is also 2. The cycle AB, the cycle 1, 2 and so on n, if B minus A, n is equal to 1, then the size is 2. Next we see the group An, n is greater than or equal to 3, the generating set is 3 cycles, then the size is n into n minus 1 into n minus 2 by 3. The cycle 1ij's, then the size is n minus 1 into n minus 2. The cycle 1, 2i's, then the size is n minus 2. The cycle I plus 1, I plus 2 is generating set, then the size is n minus 2. We are seeing the group An, n is greater than or equal to 3. If the generating set is the cycle 1, 2, 3, the cycle 1, 2 and so on n, if n is greater than or equal to 4 odd, then the size is 2. The generating set is the cycle 1, 2, 3, the cycle 2, 3 and so on n, if n is greater than or equal to 4 even, then the size is 2. Now take the group SL2 of integers. The generating set is 2 by 2 matrix 0, minus 1, 1, 0. 2 by 2 matrix 1, 1, 0, 1. Then the size is 2. GLN of R real numbers SLN of real numbers, then the generating set is elementary matrices, the size is infinite. We know very well that the generators can form a group. So, now let's see those groups. First, cyclic group. A group that is generated by a single element is called cyclic. For example, integers under addition EG plus is a cyclic group with the generator singleton set 1 or singleton set minus 1. Next, the commutator subgroup. Let G be a group and A, B belongs to G. The element A, B, A inverse, B inverse is called the commutator of G. The subgroup generated by the set of all commutators of G is called the commutator subgroup of G. And another group is finitely generated group. Every finite group is finitely generated since generator of G is equal to G. The integers under addition are an example of an infinite group which is finitely generated by both 1 and minus 1. But the group of rationals under addition cannot be finitely generated. No uncountable group can be finitely generated. For example, the group of real numbers under addition is R plus. Different subsets of the same group can be a generating subsets. For example, if P and Q are integers with GCD of PQ is equal to 1, then the set PQ also generates the group of integers under addition. Some remarks of finitely generated groups are as follows here. The remark: a finitely generated group is at most countable, so an uncountable group is not finitely generated. The group of rational numbers Q is not finitely generated. A finite set of rational numbers has a common denominator, say n, and the subgroup of Q generated by these rational numbers, that is their integral multiples and sums, will only give rise to rational numbers with denominators dividing n. But we know that not all rationals have such denominators. For example, 1 by n plus 1. So, Q does not have a finite set of generators as an additive group. Let us find out the generators of the following example. See this, the infinite abelian matrix group, the set of 2 by 2 matrix A, B, 0, 1 such that A is equal to plus 1, minus 1, B belongs to the integers Z is finitely generated. Since the 2 by 2 matrix 1 by 0, 1 is equal to B times of the 2 by 2 matrix 1, 1, 0, 1 and minus 1, B, 0, 1 is equal to the product of these two matrices is the matrix 1B 0 1 and the minus 1 0 0 1 the matrix is equal to the matrix minus 1 B 0 1 is equal to B times of the matrix 1 1 0 1 the matrix minus 1 0 0 1. This group has generating sets the 2 by 2 matrix 1 1 0 1 the 2 by 2 matrix minus 1 0 0 1. So finally we have come to the conclusion of this module. Before finishing the session, let us recall the concepts once again. First, we have started this module with the definition of subgroup generated by a subset. After that, we have seen some notes based on the generating set with an example. And then the generating set of Sn are briefly discussed in the results. And also we have seen that the generators are forming groups. Finally, we have concluded this module with an example of finding a generating set of infinite abelian group. So, I hope This module have given a basic clarification about generating sets. We will see in the next session. Thank you.